Um, I'll make myself a little bit bigger. Right, so let's just have a recap of linear search. So linear search, right, main points. Whenever we're describing these algorithms, remember, so we need to say, where does it start? So it processes a list or an array. The array, I'll refer to it as an array. The array doesn't have to be in order, so it can be a jumbled list of values. So that's how we might start. How does linear search work? So well, we can search a list or an array. So and it doesn't have to be in order. That's one of its key qualities. Linear search is something that the binary search can't do. Can't process unordered data. We always start with the first item, the first element. And all we do is we check to see if it's the thing we want. So if the element is the search item, and then we say if it is, stop. If it isn't, move to the next. Next element. If we get to the end of the list, then not found. Okay, so whenever we're describing an algorithm, so in general, describing an algorithm, we need to say what does it work with? So that's what data, what format. Where does it start? How does it do its job? So what is the process? And how does it stop? How does it end? And it might, oops, it might be that it ends two ways. Like, so linear search ends when we find the item and it ends when we get to the end of the list or the end of the array. If it doesn't stop, then there may be a potential problem with the algorithm because most algorithms need to like start, do something, then finish. It's not always true. If you think about, there is one process that we've studied where there is no stop, and that is the fetch execute cycle. When we just keep fetching instructions, and even if we tell the CPU to halt, actually it just sits there doing nothing. It's still, it doesn't fetch instructions anymore, but it just executes nothing, doesn't do anything, waiting. Okay, so in general, that is what we need to describe. So if ever has to describe an algorithm, it must contain those four elements. Okay, so just as a quick example, so, and this is what you're going to get to do for start of Tuesday's lesson. If I have got this list of numbers, and I am looking for the number 2, so search for 2. What I need to do is make sure that I write down some element positions, some indexes. Okay, so there are 6 items in here. I'm going to start at 0, and I'm going to say I'm going to go Bennett, is 4 equal to 2? And I'm going to say no, move on. So I'm going to then look up and say, is 5 equal to 2? And I'm going to say no, move on. So next position. So I might put that. So I'm going to say move on. Next position. So I'm being explicit about what I'm looking at next. And I say, is 2 equal to 2? Yes. Item found at position 2. Stop. And that's it. So I'm just making sure that what I do when I go through this process, that I am being explicit about how I'm performing the search. Don't just say, oh, just keep looking until we find the 2 and we find the 2, which is what some people will do. And that would be wholly wrong. Okay? There is no other sensible way of doing it. As long as you are clear about the steps. So where did I start? What am I looking at? What are the tests I'm doing to decide whether I've found the item I'm looking for? Okay. Right. So let's have a look at binary search, and then I'm going to leave you to do some questions. Right. Okay. So I'm going to talk about binary search. So I'm going to look at this. Like, what does it work with? So it'll search a list. Oops. So it searches a list array, but the list or the array has to be in order. Whether that's ascending or descending doesn't matter, but it has to be in order. Can't search unordered data. That is its Achilles heel. It can't do that. It's super quick binary search, but it can't. Right, so the process is we start at the middle value. That's why we need it in order. If the item we're looking for is there, if the item at the middle is search item, we stop. But if it isn't, we have to do a further test. So we need to say if item at middle is larger, and this is where the ordering comes in, is larger than what we're searching for, that is becoming a real big problem for me, that missing out ease. So if the item at the middle is larger, then that means anything to the right of that middle item is also going to be larger, and there's no way the thing we're looking for can be found. Okay, so what we need to then do is we explore the left-hand side of the remaining array. And it's easier to show when you do the working out than actually write it in English. If the item at middle is smaller than what we're searching for. Then we're going to explore the right-hand side. Right, in order for this to work, we have three values. We have a left pointer that marks the left-hand side of the list. We have a right pointer that marks the right-hand side of the list, which is, and really, you might go, yeah, oh, it's obvious. Yeah, it is, because I've used the name left and right. If I'd have called them Trevor and Derek, then you might be wondering what the hell Trevor and Derek represent. But because I've named them carefully, then I've given them meaning. Okay, so that's a really good example of naming things carefully. And we have a middle pointer that marks the middle item between the left and right pointers. And that's the crucial bit. Okay. Right, so we can calculate M by adding left and right together and then dividing by 2. And when we say that, we mean integer division. And the reason we use integer division is because we can implement integer division really quickly by doing a right shift one place, which is why shifts are important. And you know that because most of you have nailed that bit down. So you can do really quick. One of the quickest instructions that a CPU can do a shift. All right, so there is very little cost to calculating a division by 2. Okay, so in order to show how this works, what we need is some data, but the data has to be in order. So I'm going to, and they'll ask that in questions. They'll give you some data and say what search algorithm might you use. So you need to be really careful that they don't try and catch you out. Right, in order to do this, you've definitely got to put the index numbers on. Okay, so there are 8 items in this list. So this is the index. This is the data. So we're first off, we're going to set left and right pointer. And we're not going to keep writing left and right because that's too long. So I'm just going to say L equals 0. That's the left hand of the list. R equals 7. So our first calculation is to say middle equals 0 plus 7 divided by 2. So when we do integer division, we throw away, it's a truncation. So we actually, that equals 3. It is 3.5, but because it's integer division, we just truncate. Okay, it's the quickest way. So we get 3. So we say, right, let's say we're searching for, I'll do 2. I'll do one that exists, and then I'll do one that doesn't exist. So let's search for 2. Okay, so we're searching for 2. Didn't affect this because that was just a setup. Right, so we're going to say is 10, because it's the item, so it is, make it more explicit, equal to 2. So I'm actually, in fact, I'm going to write that a little bit more formally. I'm going to call this list data. So I'm going to say if data, so the name of the list, at m, is that equal to 2? And we can see that actually that value is 10. So I'm trying to be really explicit to the exam board. And I say, right, well, no, it's not. So we go on to our next phase and we say, right, okay, is 10 bigger than 2? Yes, it is. So what we're saying is this part of the list, all of those are bigger than 2. These are greater than 2. There's no way 2 is going to be in that. So we can use a bit of intelligence, which is what binary search is doing. So it's saying, well, it must be in this side then. So what we need to do is explore the left-hand side of the list. So we can say data m, which is, we know is 10, is greater than 2. So explore left. Now, to explore left, what I want to do, so middle is currently here. I need to make, my left pointer is here. I need, my right pointer is here, but I want the right pointer to be here. So I'm actually going to execute this command. I'm going to say, okay, right equals the middle value minus 1. So where m was 3, r becomes 2. So that puts r there. And you can see what I've done is I've discarded the right-hand side of the list. And I'm just going to do this process again. So I'm actually, it's this loop that I'm going to do. So I'm going to actually do that bit again. So I'm now going to say, and I'm just going to write it out. So I'm going to say, all right, okay, let's calculate the middle. So the middle equals left plus right. So that's 0 plus 2 divided by 2. So in this case, that is 1. So m is now 1. So we're going to say if the data at 1, which we know is 5 because we can see it. Oops. So I'm just going to put underneath 5. You could just write if 5 and compare it to 5. And that's what we're going to do. So it's not what we're looking for. So again, we're going to say, right, okay, let's have a look. We're going to say, right, well, the data, well, I'm not going to write data this time. I'm just going to put 5. So we're going to say 5 is bigger than 2. Okay, so we're going to explore left again. So we need to move the right pointer. So this is where middle currently is. So we want to move the right pointer to be 1 less. So we say the right pointer equals m minus 1. So m is currently 1. So that makes the right pointer equal, so I'm going to say equals 0. I've then got to calculate, oops, equals 0. I'm going to rub that out. What I've then got to calculate is the middle again. So I'm just going around the loop again. So I'm going to calculate the middle. So we're just doing this section of code over and over again. So you're saying calculate the middle based on the left and right pointer. What is the item that is at that middle position? Is it the one we want? No. Right. Well, do we explore left or do we explore right? Okay. Right. So we calculate the middle again, but this time we've got 0 plus 0 divided by 2, which equals 0. And then we can say, so data 0 this time equals 2. Oops. Keep doing that. So stop. Item found at position 0. M will always tell you where you found it when you stop. Okay. Right. Let's do that again. So I'm going to do the same numbers. So let me just grab this. I don't want to delete all that because I'll share the thing with you. I can get the numbers. Hopefully I copied all that. Right, so let's scroll my screen over. Paste that in. Right, so let's do it again, but this time let's search for and I'll do it in a more compact way. Search for, let's have 17. Right, so L equals 0, R equals 7, M equals 0 plus 7 div 2, which equals 3. Okay, so we're going to say, right, okay, what's at 3? So, data 3 equals 10. 10 is less than 17. So we're going to explore right. So this time, so we've got left is there, right is there, middle is here. We're saying, right, well, we're looking for 17. 10 is smaller, so all this lot is going to be smaller because it's in order. Okay, so we're going to explore right. So we then say, right, okay, so right equals 7, but we now need to move the left pointer. So the left pointer needs to go there. You can see physically that's where we want it to go. So we can say left equals m plus 1. That's where we put it. So that equals 4. Let's calculate the middle again and go around this loop process. It's quite a short process, binary search, to be honest. So m is now 4 plus 7, numbers are getting harder, divided by 2, which is 11 divided by 2, which should give us 5. Remember, it's integer division. Just drop the fraction part. Okay, so the data at 5 equals, so that's where middle's just been calculated, is 13. 13 is less than 17, so we're going to explore right. I don't know why I've done a massive X there. Okay, so we're exploring right. So we're going to calculate and we're going to move left across. Okay, so this time we're going to say, right, left is m plus 1. So m is currently 5, so that's going to be 6. Okay, so we've ended up, we now calculate m, so that's going to be 6 plus 7 divided by 2, which hopefully you can all see is 6. So m becomes there, which weirdly is where left is. Okay, right, okay, so the data at 6 is, what was it, 19? It's going off screen, let me zoom back a bit. So the data at 6 was 19. Right, that is bigger. 19 is bigger than 17. So we need to explore left. So we're just following the algorithm. But this is where the algorithm gets tasty. So if we're exploring left, we need to move the right pointer. So we say right pointer equals m minus 1. So the right pointer is currently 6. So r is going to be 5. Now, this is our stop condition. So we've actually got L equals 6, R equals 5. If we get this situation, so if the right pointer is less than the left pointer, we stop. We've exhausted the list. That's our secondary stop condition. Okay, the item is not, does not exist because the 2 pointers have passed. So you can see that this is the state we're in where we've gone like that. We can't calculate the middle value. Well, we can, but we're going to end up going back on ourselves and we'll just get stuck in an infinite loop unless we test for this condition. Okay, so we have a, you'll see when we look at it at A level that we have a while loop controlling this that's saying while the left pointer is less than or equal to the right pointer. Okay, or you can say while the right pointer is is greater than or equal to the left pointer. It doesn't matter which way around you do it. Item not found. So it's important that you can exit the binary search both ways. So when we found an item, we can return and we can say, oh, we found it there. When we haven't found an item, we can say we stopped because the 2 pointers flipped. That the right pointer is no longer to the right of the left pointer. You can show that diagrammatically, and you can say, oh, not found. But nicer to state it, to say that they've switched positions. It's no longer a right pointer, it's ended up smaller than the left pointer. Okay, right, so I'm going to stop that there, and I'll upload